Hello guys, I wanted to briefly talk about vectors. One of the things you should review for vectors is your right triangle trigonometry. You should recall the ratios, the sine, the cosine, and tangent of an angle, the ratios. So right here we have a right triangle, and we have the angle theta. Remember, the tangent of the angle is equal to the opposite side from the angle over the adjacent side. It's that ratio. The cosine is the adjacent over the hypotenuse. And the sine is the opposite over the hypotenuse. You should review these ratios. And if you remember SOHCAHTOA, sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. They're ratios that relate the length of the sides divided to the actual trig function of the angle. It's a way of going from the lengths of the sides to the angle, or the angle to the lengths of the sides. So you can also solve for what's called the inverse tangent or the arctangent and actually get the angle. If you know the ratio of the lengths of the sides, say opposite to adjacent, and you take the inverse of that, you will get the angle. And normally we'll be in degree mode on our calculator and we will get our answers in degrees. But sometimes we'll use radians, and we'll talk about that later. You can also write these relationships up here as this, where you're solving for the length of a side. We normally do this in physics. Like if we want the adjacent side right here, we would take the hypotenuse length and multiply by the cosine of theta. If we want the opposite side, we take the hypotenuse and multiply by the sine of theta. We normally use this format to find the components of a vector, if you recall that from class. So we use those bottom two a lot in physics. Also, to get the hypotenuse, we'll use the Pythagorean Theorem. Remember, c squared equals a squared plus b squared. I just changed the notation here. The hypotenuse will equal the square root of the adjacent side squared plus the opposite side squared. Those are the legs of the right triangle. So yes, we do live in a 3D world. Vectors represent quantities that cannot be completely described by scalars. They're quantities that have both magnitude and direction. And that is the key idea of a vector. If you look here at the bottom, vectors are quantities that we will use to completely describe quantities that need more descriptors. Magnitude, remember, is a numerical part plus a dimension, like 5 meters. And then when you add direction, you would have a displacement vector. Another example would be 3 meters per second. And when you add direction, say 3 meters per second due north, you'd go from speed to velocity. Direction does matter, so when we have to include direction with the magnitude, those quantities, we refer to them as vectors. So we can represent a vector with an arrow where the length will be the size or the magnitude of the vector, and obviously the direction it points is how it's oriented with the page where the arrowhead is pointing. That's the direction. Also, you can represent a vector coming out towards you or going into the page with dots and crosses. A dot would mean it's coming out of the page. That would be the arrowhead, and the tail would be a cross. Sometimes we have to do that. Now here's a vector in 3D space. Notice we have the XY plane here, and then we have the Z axis. And we could give its direction based on the axes here, and the magnitude would be the length of this vector. The tip of this vector could represent all points in space. Here's a vector in 2 dimensions in the XY plane. This is a position vector. We call it vector R. Sometimes it's referred to as a radius. If you were to rotate it into a complete 360, you would form a circle. But it's actually a position vector. It'll have an x-coordinate and a y-coordinate that'll give the point at the tip of the vector. And we're going to use unit vectors to describe both the magnitude and direction of what are called the components of this vector. The component of this vector, well, it actually has 3 components. One component's not shown here because we're not doing this in 3 dimensions, but it has an x component, which is just the projection of this vector onto the x-axis. What you do is you drop a perpendicular down. It's as if it's casting a shadow, and this is the x component of the vector would have a magnitude x, whatever this length is, would be its x coordinate. And this is a unit vector, which equals 1. It's called x hat or x roof. And it just means that this vector is in the positive x direction. Similarly, over here we have y hat. This means the vector is in the positive y direction. So if this point right here represented 3 and 4, x equaled 3 and y equaled 4, I could say the position vector r equals 3x hat plus 4y hat. And if you remember from your geometry classes, that would be the carpenter's triangle if this is a 90-degree angle, and this would be the 3, 4, 5 right triangle. So the magnitude of vector r would actually be 5. And then we'd figure out this angle here, and we would have the direction. Here's two position vectors. Here's the initial position vector, r sub I, and here's the final position vector, r sub f. Now, originally this vector was at, say, point P, and then we went to point Q, and from the direct line distance from point P to point Q would be the displacement vector. In fact, the displacement vector here, change in r, the position vector, change in the position vector, is the final position vector minus the initial position vector. When you do vector subtraction on this, you will get this vector in this orientation. But you should think of it as going, the direct line distance going from point P to point Q. So let's look at that in a little bit more detail. If we have an origin to start our vector off, and it's pointed at point P, we could call that our position vector. And let's say we want to move from one point to another. For example, if we wanted to go from point P to point Q, we wanted a direct line displacement from point P to point Q, we would draw another vector, and this would be our displacement vector. But it would produce a new vector from here to here for a position relative to the origin. So let's look at that. Here we have the original position vector, then the displacement vector going the straight line distance from point P to point Q. When we add these two vectors using the tip to tail method or head to tail method, this right here represents that vector addition, vector r plus the displacement vector. That's called the tail to head method. We also could use, since this forms a not a right triangle, but an obtuse triangle, we could use the law of cosine, if you remember that from your math class, to figure out the magnitude of this vector. Just take a minute to look at that. So if we have two vectors, when I use this head to tail method, I could have vector A in this orientation, and then if I want to add vector B, what I do is I slide the tail of B over to the head of A, and the answer would be this dotted line here. This would be C, and I would call that the resultant vector. So we can do this graphically. You can add these in any order. I could do B first and then A, as long as I use that head to tail method. Now I could say that A and B are component vectors, but usually when we use the word component vectors, we're talking about the x and y components. And this, I'm using this term loosely here just to explain this. And then the answer would be the resultant vector. But typically we use the word component when we're talking about x and y components. So we can add countless vectors this way, tip to tail or head to tail. Here's an example in the book. These are displacement vectors. Got vector A plus vector B plus vector C equals vector D. This person is literally walking 5 paces due north and 3 paces due east and 4 paces to the southeast. And the net displacement is from where they started to where they end at direct line distance. But you could add these graphically, and then you could, if you drew this to scale, you could measure the length of this to get the magnitude of the vector, and you could get a protractor out and measure this angle here. It would be so many degrees north of east. So many degrees north of east. Now, yes, there is a negative vector. If you add a positive and negative vector together, you get 0, or you could call it the 0 vector. What does it really mean? It means the vectors are equal in magnitude but opposite in direction. Sometimes we say these are anti-parallel because they're 180 degrees apart. When we subtract them, we will get 0, or the 0 vector. So negative a equals the magnitude of a. They have the same magnitude but opposite direction. But graphically, this is how you would draw it. So if we want to do a vector subtraction, we'd look at the vector b and then we'd draw its opposite. Its opposite would point in the opposite direction, and then do the tail to head method. And then vector d, graphically, this would be the difference between those two vectors. Also, we can do scalar multiplication. If we take a vector and we multiply it by 2, it just makes it twice. It makes it twice as long, twice the magnitude. If we multiply by a -1, it just reverses its direction. That's scalar multiplication. There's also the dot scalar product and the cross vector product, and we'll talk about that shortly. So what's R2 minus R1? If we called R2 the final position vector and R1 the initial position vector starting at this origin here, then the displacement, remember the displacement would go from R1 to R2. So what is it? Well, if you look at negative R1, wouldn't we take R1 and reverse its direction and do the head to tail method? Yes. Let's see what would happen there. All right. Here's the displacement vector, the direct line distance. But you could also represent this in a different way. You could represent it as reversing R1 and connecting it here. And then the displacement would go from here to here. Can you imagine that? There, let's look at it this way. So R2 minus R1. Remember R1 pointing in the opposite direction, but I'm doing the tail to head method. And then this would be the answer. Take a look at that. That's how vector addition works and vector subtraction. Remember, subtraction is really add the opposite, add the opposite. All we're interested in the magnitude and direction of the vector. We can move these vectors around in space, and they're the same mathematical quantity as long as we keep the same orientation and the same size. Here's an example of position vector. I have 3 position vectors here, but if I was just given the magnitude of the vector, 0.5 miles, I wouldn't know where the library is. I'd want to give the direction as well. And once I give the direction, then it would be clear which way this person would need to walk to find the library in a direct line distance. Here's another position vector. And notice that this is showing how I could break up this position vector into an x component and a y component and still achieve the same results. Notice it forms a right triangle. There's other vectors I could add to get to the library doing the tail to head method. I could draw a vector from here, Birch Street to Walnut Street, and then go from Walnut Street to 6th Avenue, and then 6th Avenue up to Maple Street, then Maple Street all the way over to the library. And that'd be all tail to head position vectors. I'd still get the same result. But normally what we do is we take one vector and we break it up into an x component, a horizontal component, and a y component to produce the same effect. We call it the decomposition of a vector into its components. Here's a picture from your book. You want to figure out the net displacement for moving the knight, which looks like a horse. Remember, you can go up 2 over 1 or up 1 over 2. And what would be the net displacement here? This is a problem in your book you should think about and see if you can figure this out. But these are displacement vectors, right? So let's look at vectors, some handwriting here. Here I have vector 1, A, vector 2, B. When I add them together, I get vector R. Notice I could do it in reverse order. I could start with B first, right here, and then add A, and I still get vector R. It still has the same magnitude and the same direction. That's tip to tail method. Scalar multiplication, I could reproduce all these vectors here. If I know what vector A is, then 2A would be the same vector, but in the same direction, but twice the size. 1/2 A would be 1/2 the size of A. Negative A is just the same vector, but in the opposite direction. Negative 3A would be the same vector in the opposite direction, but 3 times as long. So that's scalar multiplication. Here is subtraction. I got vector A and vector B added, and here I have vector A and vector B subtracted. Notice the orientation of the resultant vectors. And here are the unit vectors. Remember, unit vectors are just trying to show direction. They have a magnitude of 1. And if they're positive, it means they're in the positive x and y direction. Also have the z direction. It would be a vector coming out of the page. Now, normally, many physics books, we use x, y, and z for the unit vectors, and they're pronounced x hat, y hat, and z hat, or x roof, y roof, and z roof. I like hat better, x hat, y hat, z hat. Other books use I, j, and k for their unit vectors, but it's the same thing. Now, if I had negative x hat, that would mean the vector's pointing in a negative x direction, negative y hat, negative y direction, negative z hat, negative z direction. Now, the z-axis comes straight out at you from the origin. We use these to show direction. We'll skip the cartoon. Now, normally what we do is we take a vector, any vector A, and we decompose it into its x, y, and z components. So it'd have an x component, and there'll be an x hat, a y component, a y hat, a z component, and a z hat. So decomposing these vectors into their unit vectors, into their magnitude and direction, we're going to use the unit vectors for the direction. There's how you pronounce them again: x hat, y hat, and z hat. Remember, it has a magnitude of 1. All right, here's a vector in 3D space. It'll have, if we do a projection onto the axes, it'll have an x component, a y component, and also a z component. And we could figure out these angles here with the different axes. And we could locate any point in space by using this method. So vector A is projected onto the 3 axes. We're going to typically stick with 2 dimensions, so we'll have an x component and a y component. And we could get this angle by using trig functions. We see a bunch of right triangles in here. We could use the cosine of this angle and figure it out this way. We'll do this later. Right now, we're going to stick with 2 dimensions. So here's a generalized vector in 3D space. Notice the angles, how they're given. We'll come to this later. We're going to stick with 2 dimensions at the moment. So here's our 2-dimensional plane, our xy plane. We have the x hat, y hat unit vectors. We could apply this to a baseball diamond. This is one of their homework problems. If I want to know the position vector for going from home to first place, well, I could imagine a vector going from home to first place and put an arrowhead here. And how would I write that vector? Well, couldn't I write that vector as 90 feet in parentheses x hat? Yes, I could do that. 90 feet x hat. It doesn't have any y direction or z direction, so I ignore it. How about going to third base here? Well, it doesn't have any x hat. I would just write that as 90 feet y hat, 90 feet y hat. And what if I went from home plate all the way to second base? What would I call that vector? Well, I'd look at its x component, 90 feet x hat, plus 90 feet y hat. 90 feet x hat plus 90 feet y hat. That's how I would write it. There's a homework problem like that. You should do that homework problem. So here's this notation. Like for the baseball example, I'd have for a double, if this represented the vector going from home plate to second base, this would be 90 feet x hat plus 90 feet y hat plus 0 z hat because we're in the plane. So 90 feet x hat plus 90 feet y hat. Or you could write it without the units, 90 x hat plus 90 y hat. The magnitude of the vector is written typically with absolute value symbols. Sometimes you double these absolute value symbols, but the magnitude is just the size of the vector with its unit, so like 3 meters or 90 feet. But when you add the unit vectors, then you're giving the direction based on the coordinate system. Also, when you want to find the magnitude, we typically use the Pythagorean Theorem. And if it's in 3 dimensions, it would look very similar to the Pythagorean Theorem, but it would add the z-axis. So instead of just being, the typical c squared equals a squared plus b squared, well, we have another term here, but this works. So we take the x component square it, the y component square it, and the z component square it, add them together and take the square root. We're just using the x and y components right now, so this would be 0. But that's the Pythagorean Theorem. So if we're going to decompose a vector, we take a vector, we break it up into its components, it forms a right triangle. We find the x component by taking the magnitude of the vector and multiplying by the cosine of the angle, if it's set up this way. Remember, in the right triangle, there's 2 acute angles. Be careful what angle you're using. If you're using the angle up here that's not shown in this formula here, it reverses the sine and cosine. But using the one that's shown, the x component will be the cosine of the angle, and the y component, y sin, will be the sine of the angle. So it's always magnitude times either sine or cosine of the angle to get these x and y components, the way that we're setting it up. And to get the magnitude of the original vector, you use the Pythagorean Theorem. And to get this angle, you'll typically use the inverse tangent or the arctangent of the opposite over adjacent sides. And this is normally what we do when we're decomposing a vector. We'll apply this. This is right triangle trigonometry, what we started off with SOHCAHTOA. Okay, I think this is a good time to stop at this point. There's a lot more here, but let's just stop this right now, and then we'll continue later.